Hello and welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we will learn about estimating using confidence intervals. Okay, so let's first talk about what in inferences. So when we are trying to make an inference about a population parameter, we can do it in two ways. We can either estimate the unknown value of the parameter, or we can make a decision about some hypothesis about the parameter. Let's look at an example to differentiate between the two. Let's say, so the first part where is we can estimate the mean time mu for an industrial robot to complete a task. So that would be estimation, or we might want to decide whether the mean value exceeds, let's say, 3 minutes. So that would be hypothesis test. So in this chapter, we will learn estimation techniques using confidence interval. And then the next chapter will be Chapter 8 will be hypothesis test. Let's start with a very basic idea of estimate. So let's say we want to estimate the value of a population parameter. The easiest way would be to gather a sample from the population and then calculate a point estimate, which would be a single number which results from the calculation. And this would be a point estimate. So for example, let's say we were interested in the mean mu of a population, and we pick a sample from that population and calculate the sample mean x bar. Then the sample mean x bar is the point estimate of the population mean mu. Okay, let's say in general the population parameter is theta, and this theta could be the mean mu, it could be the population variance sigma square, or we could be interested in the probability of some observation that is selected from the population. So all these could be answered using a point estimate. Okay, now if we use theta as our parameter, then the point estimator would be denoted with theta, and we put a small hat on top, and that would be our notation for the point estimate. Okay, so there will be a rule or some kind of formula that we use on the observations in the sample to compute a single number, which will be the estimate of theta. Okay, here's an example. Let's say we have a random sample of n values, y1 through yn, for a variable y. Then the sample mean y bar is a point estimator of the population mean mu. The sample variance S square is a point estimator of the population variance sigma squared. So it's kind of intuitive. Okay, now we discuss the idea of a sampling distributions. Let's put it together here. So when we have a point estimator from the sample, that point estimator will possess a sampling distribution. We discussed the idea of sampling distribution. It is the distribution of that sample statistic, which is obtained for a large number of samples from the same population. And this sampling distribution will describe its properties, which is the shape and the mean and the standard deviation. Now for the mean, we can use the central limit theorem. And using the central limit theorem, we know that the sampling distribution for the sample mean will be approximately normally distributed. If the sample is large enough, let's say n is 30 or more, the mean will be mu and the standard error will be sigma divided by square root of n. Now, if we take this sampling distribution and if we go by two standard deviations or two standard errors on each side, remember it's sigma divided by square root of n. So 2 times sigma divided by square root of on each side, then this is what the distribution will look like. So we have mu in the middle, and then we are going on each side by 2 times sigma y bar, or the standard error. So this is approximately 95% of the area. Okay, so this idea, this distribution of the sample will be used now to create an interval estimator. Now, what is an interval estimator? An interval estimator is a pair of random variables obtained from the sample data. So instead of a point estimate, one single value, we have an interval, a range of values as an estimate. So instead of saying that the approximate or the um, mean value x bar is 3.5, let's say, we will give the inference or the estimate in terms of an interval. We will say that the true value of the mean is between 3.2 and 3.8. So it's instead of one value, we have an interval. Okay, so this interval basically will be again a rule which we will use to where we'll use the sample observations to calculate this interval. And we want this interval to estimate the parameter with a high degree of confidence. So basically, something like we create this interval and then we say, okay, we are 40% confident that our value is in this. It's not of much use. We want a higher value or higher degree of confidence in the interval. And the resulting interval that we create with this high value of confidence is called a confidence interval. Okay, and the degree of confidence that we use for that interval is called the confidence coefficient. So typically we will decide this number before creating the confidence interval, and typical numbers are in the 90s. So 90% confidence interval, 95 is pretty standard, and then we have 98 and 99% confidence intervals. Okay, so here's an example. Let's say if we create a confidence interval where the confidence coefficient is 0.95, then we call it a 95% confidence interval. If the confidence coefficient is 0.99, the interval is a 99% confidence interval. Okay, now let's see how we can find this confidence interval. So one way is to find the confidence interval, and we will use the generalized parameter theta is to acquire a pivotal statistic. Now that statistic is a function of the sample values and a single parameter of theta. So basically we pick a sample from the population and we calculate this pivotal statistic, which is a single value. Many of the statistics that we will see are approximately normally distributed. So if we have a large enough sample size, the central limit theorem applies to a lot of these statistics, and we can create this confidence interval using the expected value, using the standard normal distribution of this pivotal statistic. So let's see what pivotal statistics are. Let's say this is how we can generalize it. So to illustrate, let's see there is a statistic with a sampling distribution, and this sampling distribution is normally distributed for large samples. The mean is expected value of theta hat. This hat on the top indicates that this is a statistic. So expected value of theta hat is equal to theta, the mean, and the standard error of sigma theta hat is equal to is the standard error, and we have to figure out for specific cases. Now, because it's normally distributed, we could use the z-score transformation here. So theta hat minus theta divided by sigma of theta hat. So mean of the sample minus mean of the population divided by the standard deviation of the sampling distribution. Now this distribution is now a standard normal distribution which can be used to create a confidence interval. This z value here is a function only of the sample statistic and the parameter theta, so we can use this as a pivotal statistic. So basically we will have a distribution of this pivotal statistic, and then depending on the confidence level, we can create the confidence interval. So let's kind of see it visually what we are trying to do. So we have our parameter theta, we have the statistic theta hat, and we make the z-score transformation that gives us the Z distribution. So let's say we wanted to create a 95% confidence interval. That means we are interested in these two values here with 95% area in the middle. Let's say we were interested in a 90% interval. So we are interested in these two values here with 90% area in the middle. So that would be our confidence interval. Now, the question is, how do we figure out these two values? So we will first use it in a generalized format, and then we will use it for specific statistics. So here is how we can start. So this area in the middle is, let's call it 1 minus alpha. Okay, so this is 1 minus alpha in the middle. Then area outside this is alpha. And because of symmetry on each side, we have alpha over 2. Okay, so this is 1 minus alpha, alpha over 2, alpha over 2. The total is still 1. So the probability of Z between negative Z alpha over 2 and positive Z alpha over 2 is 1 minus alpha. So that's kind of our starting point. Okay, and this alpha value can basically vary. Now, making the Z-score transformation here, so we can use theta hat minus theta over sigma theta hat instead of the Z. Then you take the sigma theta hat on the other side. Okay, move it from the denominator here, and also subtract the theta hat on each side. When you simplify it, you will get the two values here. Theta hat minus Z alpha by 2 sigma theta hat, and then theta hat plus Z alpha by 2 times sigma theta hat. So these two values here correspond to these two numbers here, this number and this number. So this will be our confidence interval. So the lower limit, also called the lower confidence limit, can be calculated as theta hat minus Z alpha by 2 times sigma theta hat. And the upper limit will be theta hat plus Z alpha by 2 sigma of theta hat. And this will give us a confidence interval with a confidence coefficient of 1 minus alpha. Okay, so if 1 minus alpha is 0.95, then it's a 95% interval. So we can use this generalized format for specific parameters. We can replace the theta hat with x bar and sigma theta hat with the standard deviation or standard error for the sampling distribution of the mean, and that will give us the confidence interval. Okay, now let's put it in the format of a theorem, theorem 7.2 in the book. So for a large sample, 1 minus alpha times 100% confidence interval for theta can be summarized as, so theta hat, which is the sample statistic, is normally distributed for large samples with expected value of theta hat equals theta. So that's the mean, and standard error given by sigma of theta hat. Then the confidence interval will be theta hat plus and minus Z alpha by 2 sigma theta hat. Okay, so this is the generalized format, and we will use this to create our confidence. We don't have to prove it every time. We will just use the theorem directly. So out of this information, this will be from the sample, this will be from the sample. The only thing that we need is the Z alpha by 2. So let's see how we can calculate the Z alpha by 2. The Z alpha by 2 can be calculated from the table. So if you think about it in terms of the distribution, what we have is, if you look at the middle is let's say it's 0.95 for a 95% interval. If we divide it by 2, we have 0.475 to the right of the center, and then we have the remaining piece, which is 0.025. Now, if you look at the table, if we have to basically look for 0.475 within the body of the table, and you will see that it corresponds to a Z value of 1.96. So right here. Okay, so 0.275 corresponds to 1.96, and that is the z alpha by 2 value for um, replacing here. If you look back again at the figure, the diagram, so this is 1.96 and this is negative 1.96. So depending on how much area is in the middle, we can figure out the z alpha by 2 value. Again, so this is for now, this is a generalized format. What we will do is we will look at specific parameters, and we will create the formula or derive the formula for the confidence interval. Some of these will be the one that we just derived here, this formula, and then find the z alpha by 2 from either the z table, and I'll show you a shortcut to find it from the t table, and then just create the interval. So that's in general what a confidence interval is. In the next lecture, we will discuss specific parameters and find the confidence interval. All right, thanks for watching, and see you soon.